a little bit of background of who we are. We sell 3D printers. We're based in Redwood City, California. We've got about 230 employees now. We've raised $221 million in venture funding, and so it's definitely been fun ride. But what got us into it was essentially three main problems that we saw in 3D printing. One was that 3D printed parts, they take forever. The printers are very slow, they're not economical, and it doesn't make sense. The other one was that 3D printed parts are mechanically weak. This is not so much a problem for the metals, but on the plastic side, polymers derive all their strength from chain entanglements. They have memories of their prior form. So if you're laying down a material layer by layer, you're going to have poor interfacial adhesion between those layers. Or if you're sintering particles together, you're going to have poor interfacial adhesion between those particles. And that was something that is a big problem with additive as well. And the other one was the material choices are far too limited. And this is more of a cultural statement around the industry. The industry for a long time relied on the large chemical companies to do R&D development for them. The chemical companies, that's not stuff they do well. They are used to shipping things in tanker cars. Doing things in low-off volumes is not something they were interested in. And so we thought that we could attack those main three topics. And so on the TED stage in 2015, we launched our process, which we call CLIP, Continuous Liquid Interface Production. It was a continuous process, so no longer layer by layer. And it's made up of three main components: a stage that the part actually adheres to, a projector that's very similar to what you'd see here in the room today, and then the window. And the window is really the secret sauce behind the printing process. That window is not only permeable to light, but it's also permeable to oxygen. Think a contact lens, if you will. Oxygen inhibits polymerization from happening, where light causes it to react. So right at the surface of that window, right where the light is most intense, we maintain a constant liquid interface all the time that allows us to go in this continuous printed fashion. What does this look like in real life? This is called an OTC measurement. It's actually, imagine sonar with light, and you can see the dead zone right at the surface of that window. That dead zone is roughly 60 to 100 microns, depending on the material that we're using. You can see the resin flowing through the gap, and this is what it actually looks like. So this part is about 2 millimeters in diameter, and it's printing at about 200 millimeters an hour. So that's a real-time image or video, and is what we do. Now, there's several advantages also beyond just going fast. It is very common in additive, if you look through the literature, where you have variant mechanical properties. Depending upon the orientation of the build, you're going to get different mechanical properties in each of those directions. That's a major problem. If you're doing things like lattices, if you're doing things that need to have certain force requirements associated with them, you actually need to think about what orientation you're building in order for the end-use application, which is rough. If you're doing lattices, it's almost impossible. You have all those struts going in different directions. Each one is going to break at a different point. Going continuously means that we have invariant mechanical properties. So no matter what orientation you build in, you're going to get the same mechanical properties in each of those directions, which is a big deal. That allows you to actually do simulate how the part is going to perform before you make it, which is something that not many people can do in the additive space, in the plastic additive space. One of the other things is that we pioneered was it allowed us to get into a whole new world of chemistries. If you could just go faster and you were using the same stereolithography resins that everyone else was using, it wouldn't buy you much. You can prototype faster, but so what? That's not why we were here. Our goal was to figure out how to get thermoplastic properties out of a stereolithography machine. And so we developed a process that we call programmable liquid resins. Essentially, we use light to lock shape, and we use a secondary chemistry through a thermal process to actually provide its mechanical properties and create those chain entanglements. And so you see vastly different mechanical properties after print and post-bake. An example is the cyanate ester material. In the green state it comes off, it's about 250 to 280 megapascal modulus. After the bake, it gets up to about 3 to 4 gigapascal. So it's a very, very different material. And this has allowed us to get into a wide range of material properties, ranging from our rigid polyurethanes, which are more akin to PCABS, ABS. They have about 120% elongation at break, very, very tough material, to our flexible polyurethane materials that's more akin to polypropylene, over 200% elongation at break. You can do living hinges, snap fit features, those types of things. Our elastomers are something that we're world renowned for. We do elastomers better than anyone. High temperature resistance and the cyanate ester for under the hood applications. We have an epoxy system that's really was targeted to replace 20% glass-filled PBT in the electrical connector space. We have many electrical connector partners. That's something that we do very, very well. We have a new material releasing actually this quarter, which is our new silicone material. This is a soft durometer elastomer, mainly angled towards consumer products as well as the healthcare space, and as a clear rigid polyurethane. So the same toughness that you would expect from our polyurethane, but in something that is optically clear, which has a lot of applications both in dental and orthodontics as well as in automotive. And what that really showed is that we were able to get a change of paradigm. When you were purchasing a 3D printer early on, you had a major choice to make in your purchasing process, which was if you wanted surface finish and resolution, you went to SLA and PolyJet. However, the material properties weren't very good. You put them out in the sun, they degrade. They were not very thermally stable. They would warp on your desk even under the incandescent lights. If you wanted something functional, you went to SLS or FDM. The problem is the parts don't look very good. They have poor surface finish. They have porosity problems. You would never see an SLS or FDM component inside the cabin of a BMW. It just wouldn't happen. And so with carbon, we were able to fundamentally change that. We get the best of both worlds. We're getting those thermoplastic properties out of that SLA at great speed, which is a game changer and what has allowed us to actually get into production. By attacking those things, that is what has enabled us to make end-use components instead of focusing on the prototyping market that has historically been there. And that's gotten the attention from many great partners, Adidas being one of them. Adidas partnered with us, and from the point when I had my first conversation to them to when they released their product was 12 months and 1 day. By the end of next year, they will be the largest user of 3D printers in the world by a long shot. And this is something that we're super excited to be on this roadmap with them. The major advantage in this space is allowing them to get through to a breakthrough design that they weren't capable of doing out of traditional manufacturing. The other advantage is they can actually get to N of 1. I can make a pair of shoes that's no longer size 12, it's size fill. And that is one of the big advantages. The other big advantage is actually, and this was sort of found after the fact, is because it's open cell in nature, it's actually about 20 degrees cooler after 2 hours of wear. So the thermal properties are way better than what you would see from a normal sneaker. So there's about 10,000 pair that will be released this holiday season. Next year will be hundreds of thousands, and then 2019 it's at millions, and our goal to be around 50 million pair a year in around 2020. So it is the largest manufacturing application by a long shot. When they're first released, they will be done in normal sizes. And then gets to the crux of this whole thing. We've gotten to production. We now have the machine and the materials to get to end-use parts. There were a bunch of other missing links. And you start to think about it. Okay, you have the printer now. You can make the parts. What then holds you back from doing N of 1 pair for the world? The problem is they have the scanning technology. Right now, they're making these designs by hand, one-off. It cannot be done by hand if you're going to make N of 1 for the world. And so the design tools needed to take a major path forward and was actually holding us back from making the value prop for Adidas even better. And so we've spent a lot of time working on our own internal design tools to help speed up Adidas's launch. However, they also have a lot of implications for outside of Adidas as well. And so we'll talk about that a little bit. The other one was in manufacturing software systems. You have a facility of 50 to 100 of these in one space. You need to have the systems that are from a QC, a quality perspective, from a tracking perspective, from an optimization of build perspective, built. Oftentimes you look to companies like Oracle and SAP and to build those things for you. However, those are very, very large companies that are very, very slow. And so we unfortunately don't have the luxury of waiting for them. And so that sort of gets into, we are a software-driven company. From the beginning, we've designed these machines to be over-air connected. They receive software updates roughly about every 6 weeks. If you talk to our customers who've had the machine for over 12 months, they'll tell you that it's night and day difference. Every day they go, it's something new and something exciting. Whether it's a new material launched, oftentimes our competitors would force you to buy a new machine in order to get access to a new material. This one printer has access to our entire pipeline of materials, no matter when they're launched, and that's a major advantage for them. The other major advantage to it is each one of these printers spits out about 1 million data points a day. We know when something's going wrong before you do. We do predictive customer support. We do predictive maintenance. They are fairly reliable machines. In the history of our company, we've had to go out 12 times in order to do a physical fix in person. 10 of those 12 times were predicted before they happened, which is a great user experience perspective. And which is why we're able to accelerate development much, much faster. This is sort of leads into this printer being perfect for developing these manufacturing systems. I know every time that printer, every activity is done with that printer, whether you are filling it up with material, whether you're removing a build platform, whether you're removing a window. I have the ability to know when track it from the stage, the printed part, through the post-processing steps, all the way through, and we've been collecting this data. And so this allows us to understand in complete deep detail the true cost per printing. Oftentimes people talk about the cost per part associated with the machine and the material. That is never just it. There is always post-processing costs associated with it. And being able to track that and monitor that, understand our customers want to know which shifts are better than other shifts and employee efficiencies. And so this allows us to monitor all of those things. It also allows us to track the part all the way through the process. So every pair of shoes that you see actually has a trace code on it. It ties it not only back to the machine that it was made on, but the lot of resin that was used to produce it, the window that it was printed on, the stage that was used to produce it, and then the frame-by-frame manufacturing data. So when we go in and we actually test its final performance randomly and we see something wrong, we can go back and look at what happened and tie it back and prevent that from happening in the future, which is something that's very, very powerful. The other thing, as you can imagine, is setting it up for a shop floor. So optimizing the machines, being able to automatically push jobs, avoid machines being down, those are the types of things that need to happen if you're producing 1 million pair of shoe a year at a 50 printer facility. And that's something that we have the ability that we're building out for the first time as well. We're building it with the mindset of eventually having to integrate with something like SAP, QuickBase or Oracle, but it's definitely something that has something that's absolutely desperately needed. Lattice design was another piece. One of our, if you're using technologies to print a block, there are better ways to make blocks, much cheaper ways to make blocks. For our technology, the more complex it is, the better it's going to be. However, the design tools haven't really caught up. And the main reason for this is there's never really been a technology that could produce something that people actually wanted. So the software companies were not putting tons of effort into this space. Now that we had that technology, the opportunities are starting to come up, and we're really starting a new phase in Carbon's world. When we first started, we were based on 3 pillars, which was hardware, software, and materials. And when I said software, it was mainly around machine functionality. It was that connectedness that I spoke to earlier. But we're starting to realize a 4th pillar that is really, really important, which is around design. And that's something that we're spending more and more time with today. That oftentimes our customers come to us and they want to be the Adidas of blank industry, right? Fill in the industry here. The problem is they don't know how to do it. And so we spend a lot of time at Carbon holding our customers' hands through that process, almost acting as their Sherpas as they go up Everest. And that's something I think that's unique to us. And one of the things we've sort of developed out of that was a really, really powerful design tools. And so historically, the conventional way to think about lattices is that they're repeating 3D unit cells. And they go over and over and over again. The problem that you traditionally see, though, is these non-conformal problems that show up, where you see the parts actually have pointed edges and so on. And so when you're putting in compression profile, and that's your output, these areas here create problems. They create collapsing, premature collapsing. And so they're actually not true to matching the compression profile. The other problem is they create manufacturability issues. The printer sees that, and it oftentimes requires you to put a support, or you need to orient a certain way to avoid that. The other problem is that aesthetically, it's not pleasing. You don't want variation to that extreme. Oftentimes these parts are wrapped in other things, and if you have points like that, it's not going to wrap well. And so we developed a conformal lattice technology that's automated, it's cloud-based, and it happens very, very quickly. Somebody asked earlier about what is your, how do you handle the large size files? Our whole system is cloud-based. So you can put a CAD file up in the space and put in your compression profile, and it will create a lattice geometry conformally to that lattice and send it to be printed. But creating the file is not the end, just the end game. The problem that you're going to see is that creating the file is just one thing. And somebody mentioned earlier about complexity being free with additive, and I love that connotation, but it's not fully true. 3D printers all have design rules just like anything else. Minimum wall thicknesses, minimum strut thicknesses, and it's dependent upon the process, and it's dependent upon the material you're using. And so those are the types of things that come into place. And so what we're trying to do is so that designers don't actually have to think about any of those things. They can put it in. We have a library of different cellular structures and compression profiles that we can match specifically to you. And not only that, but it actually simulates the parts in the cloud before they're actually printed to make sure that it's going to behave exactly how you want it. And then on top of that goes through a printability FEA to make sure that it's printable. And if the printability tool comes back and says there's some issues from a printability standpoint, it will automatically adjust the file accordingly, making sure that you're okay with it as a user. And this has become super powerful for Adidas. Adidas was our first customer that we're actually using this for. What this is allowing them to do is, instead of releasing just one product, within a year, you'll see them release 4, 5, 6 products in a very, very short period of time. That is a major, major deal. Now that you have the tool to make the parts, you need the design tools to produce the parts for that tool. And we're doing a big push into that in that direction. The other thing that comes up is around textures. People don't like the aesthetic look of the parts that are naturally 3D printed. And when you are producing a injection molded part, you create your CAD file, you go through your mold tech book of textures, you select what you want, the tools are laser etched, and you get your texture. Additive, light's a powerful chisel. We can do many, many different types of textures. And texture is a very, very important piece in the design world nowadays. It actually gives you the aesthetic of value or of luxury. It's used in many ways to help change your viewpoint of mechanical properties. And so we've had a lot of customers that are interested in doing this, and if you're familiar with the texturing tools out there that do it in CAD, one of the major problems is that it does well on flat surfaces, but when you try and do curved surfaces, it starts to fall apart. It fades in and out. And so we've created a really, really powerful cloud-based algorithm that allows you to select areas and apply 80 different textures to them. Be very, very specific in the file, and this completely hides the defects, what would be viewed as defects of 3D printing. And not only that, but within one part, I can highlight where I want a texture, where I want a different texture, and so on, and do custom textures for customers. As you can imagine, Caterpillar, John Deere, Audi, those companies have their own textures. And so we can digitize it for them so that only their printers have those textures. And what's really, really interesting is that now we're able to get to a point where the textures aren't just for aesthetics, but they're also functional as well. If you could use textures to affect aerodynamics, if you could use textures for friction control, those are the types of things that become really, really interesting. Imagine a lattice bike seat that had a texture that prevented you from slipping back on it as you were riding down the road. Or if you had textures on the helmet that were shaped like shark skin that actually helped with aerodynamics. Those are the types of things that we have the power of doing and things that we're exploring now with these tools. Also, the other thing is textures don't just have to be two-dimensional. Textures can be three-dimensional as well. This is something that we did for one of the local bike companies for us for a bike grip, and it's three-dimensional. Each one of those is actually an elastomer piece, and they sort of collapse on your own, and it gives you a soft touch feel. The other advantage is air is getting in there. You're massively helping thermals. Heat is a big problem for handlebars, and so being able to avoid those are really, really important. So the tool to do this is very, very complicated. Being able to assess a three-dimensional texture across a surface through curves, through undulations is something that not many people can do and something we're pretty excited about. So it opens up a whole new world and possibilities. Microneedles is something that is really, really interesting to us. These are small structures that are 200 microns at the base, 1-to-1 spacing, 2,000 microns tall, 1.25 micron tips, made of biodegradable systems for drug delivery and so on. So those are the types of things that you can now do with these packages. Sound and vibration damping is a huge one. A lot of people are interested in things like that, ventilation, as I mentioned before.